Now, today we are going to talk about chapter 4, and what I will try to do is actually this chapter have two main portions. So today we try to work on this example from GNU, and then it will go to semantic analysis, okay, theory. So I'll start to introduce the GNU compilers. Okay, so this portion, this chapter will be on semantic analysis. So from here, I'll first introduce this compilation flow, and that would involve this GNU compiler, and then the role of the semantic analysis. So from there, we will introduce this attribute grammar, how to create attribute grammar and attribute flow and syntax type. So then it's declaration of the grammar tree, okay? So the first portion, this compilation flow will tell you what is the purpose of the syntax tree and declaration of the syntax tree, okay? And then here we'll be talking about the importance of such declaration. And then it will be what is the declaration, and then how it works, okay? And then finally giving an example on the syntax tree declaration. So basically, this whole chapter is dedicated for the declaration of the syntax tree, and then talking about from a example, and then the theoretical background, and then to a example by the syntax. Okay. So let's see. First one, the example is not by syntax, by the real use. Okay. So okay, we get started for this chapter 4, semantic analysis. So overview of semantic analysis in compilation flow. So first we need to know about what is the structure of a compiler. So a compiler basically consists of the front end and back end, okay? And front end 3 stage, it actually work on the lexical analysis, and then syntax analysis, syntactical analysis, and then this one, semantic analysis. Okay, and then you go into the intermediate form generation that will be coming to here. So front end, your source code doing scanner, go by parser, semantic analysis, and then simple table. So this actually, as I said, is actually will be talk to each other during the process of the lexical analysis, syntax analysis, and semantical analysis. And after that, you will get something called syntax tree, okay? And it actually has annotated the syntax tree. That is decorated. So here is after declaration, you will send to instruction selection, and then try to allocate the memory. So here it may be a machine model, maybe a real instruction set, and then you do emitter and then generate the assembly code. And the assembly code may be translated to executable code depending on what is the assignment of the compiler, okay? So backend is starting from this decorated syntax tree, and then start to generate the instructions. And then to generate the instruction, you need to optimize the code. And then based on a machine model, the register files, and then you generate the code. And okay, that's the first thing introduce about the compiler. So the front end, actually you take the source code, pass through the scanner that we know, generate token string, At the same time, you may generate a simple table, but some of the simple table have to depend on the parser. So the token sent to the parser, and the parser actually will change the simple table. And some of them will help the scanner to readjust the scanner, or actually helping to build up the duo that scanner may need actually. So here, the scanner and parser sometimes will work together. And then after that, you get a syntax tree, and that syntax tree will be sent to the parsing stage, and you would pass to the syntax semantic analyzer. And during here, you evaluate the tree by the scope of the variable, by the rule, by the syntax, and then if they found there is some error, you will report. If no error, the tree will be sent to here, and then continue for the backend. Okay. So typical backend is that after the tree has been generated, your simple table and your register allocation will be here, but this one is primitive. So you will go into independent co-independent instruction set independent optimization. So you go into there, but here it's not one optimization. It may be 10 plus, maybe 20 plus optimization, maybe 100 plus optimization. Depends on which competitor you talk about, okay, and how much you would like to do. So you do GCC, there may be a flag, right? There may be a flag to have an all warning or something that actually will tell them what you need to do, and also what instruction that you want to generate, okay? And you may also have a standard, say C11, whatever. That's something, some flag you need to set in order to teach compiler how to do it, okay? And here, after you generate the intermediate phone call, you will pass through the machine-dependent stage, and you will also do another optimization. It's called pithole optimization. So basically, your instruction, maybe there are some wait stage or something, or there are some branch, and then you need to fill in non-related code, maybe from somewhere originally later pull to here or something, to optimize the holes so you get a beta code, okay? So that's here, and you also need to allocate a register. And register, because you have fixed register window or register file, so you allocate some register and some release later, some be reused. So actually that is also very important. And once you have the code and you generate assembly code, you actually will, it's ready to generate a assembly code. And up from here, we just finished the compilation stage. We haven't do the linking. So there are still some more stage after here. So GCC is a GNU compiler collection compiler, okay? It's a collection that involves compiler, assembler, and linker, okay? So GCC is not golden C compiler, okay? Some people think about it that way. It actually is GNU C compiler. I'm sorry, compiler collection. Okay, some people think that GCC is some sort of C compiler. It actually is a family of compiler, and it takes many languages. So you have C preprocessor, and then pass through the compiler, and then you put into the GCC, and you can link with different executable objective code. Okay, so here you can, this portion just generates some sort of .o code or .s code or .asm code. Okay, and that will go here and then do assembly, and then assembly, and then pass back to collection. So here you may have a collection of .o code from different source, and then you do linking, and then there's a steady linking, and maybe generate a dynamic linking file, and then eventually get prepared. And when you do building of the program, those .o code and linking library will be used to generate tactical. So here is a steady linking, and you will still go into dynamic linking stage when you run it. Okay, so static means that linking means that before you run the program, you will prepare the library, and the program will be linked together. Dynamic linking means that when you run it, you will call a DLL and actually find the tactical. Is that okay?
Yeah.
Yeah. So that's the what we have here. And static linking means what? Means actually here you have a program, and here you have another program. Say here is A.O, here you have B.O, okay? So you have some using some external variable or function here, say jump to F, okay? And then you have to be able to jump to that, and when you finish, you go back to here, something like that. Okay, so that's called linking. But when you build a .o file, you don't have that. It may be just give you a some sort of temporary edges like B module and then F function, something like that. It's okay?
Yes.
Yeah.
And when you really link it, it will be put in here with the real edges. This one will be, and it maybe is a segmentation pointer with some edges. So this edges maybe is relative edges to here, and you put here like 3355, whatever, right? But this segmentation pointer is not determined yet. Why? You just need to know where this code being loaded to. So at compile time, actually you don't know. But when you actually have your CPU, you have your memory, when you try to run it, this program will be loaded somewhere here. So your A program image, B program image will be loaded here. And then when you do something, it will be using the segmentation pointer as a relative edges, and you find the code from here. So it may not even be a fixed number. It just creates some leakage. Okay. As I said before, actually here you have, when you have a .h file, it is informing the compiler that who will link to where, and that's why you need a .h file over there. Is that okay?
Yeah.
Yeah.
Yes.
And if you look at the Java have no such a problem, because Java, as I said, it's actually based on a Java virtual machine. So your lower class being loaded here. Everything can be seen by the Java virtual machine. So your class file being loaded to Java virtual machine, another one loaded here. Okay, it's all under your program's control. You actually see everything. Is that okay? So that's totally different. And C style, fortune style, you have to go through such a linkage stage. So GNU compilation collection, GCC, provide such kind of architecture. Your input code being fit to here for, and then you will go through the parser, and then, I'm sorry, here is your source code. So your source code pass to parser and lexical scanner. Okay, that's the first thing you do. And then your language pass through here to generate to create your compiler grammars, right? And then put into those what's that? The compilation tables, parser table, whatever. So every language, different language, you may have C, you may have Fortran, you may have Ada, different language being passed through here. Okay, so that's GCC allow you to do that. But this portion will be similar as long as the grammar is following GCC rule. This one you do parser and then send to Gimbalifier and then send to tree SSA optimizer and then expander. So here your target machine and your input language provided here allows you to build up the compiler by it will automatically build up for you depending on your rules. So that's what GCC is about. So each language will be formulated here, and then GCC has one set of code to deal with this different model, and then your source code and target code is from here going through different stage and get out here. Is that okay?
Yeah.
Yes.
So GCC is a compiler system generated by GNU, okay? And GCC is a key component in GNU tool chain and the standard compiler in Unix, like let's say it's Linux. Unix actually very few now. And then GCC has played important role in the growth of free software, so it's very important. Originally, is GNU C compiler. It will need only handle C language. It's GCC 1.0, released 1986, 87. I go into college in 86, so actually I am the first group of people to try the GCC 1.0 when I was little. So yeah, I grew up, so C actually is my third language, okay, my third language, but actually it's my native tongue actually. So I take a basic as my first language, maybe about 3 months or so, Pascal, in my first introduction to programming, another semester. And second semester in college, I take this one. So that's my native language. And then after 4 years in college, I haven't learned C++ yet. So I really learned C++ after 1990s. Okay, so but GNU C compiler have been there for a long time. So Java is 1995. Eventually, when I was in PhD program already, so it was extended to compile C++, okay, and then Objective-C, Objective-C, C++, and Fortran, and Java, Ada, and Go. Objective-C is important because it's taken by these two. C++ is taken by what? By it actually is a precursor for the Swift language. So actually, Apple is using it. Right? But in reality, Objective-C++, you can also run it on GNU environment. So it's not only one language, there are several languages, and then GNU C++, 14, 17, and then now 20, okay? So it's actually a long history. So left side is machine independent, right side is machine dependent. Okay, here is another view. So your C++ language will be put into here and then generate language specific code. Okay, target machine may be ARM, maybe x86. You will have machine discretion over here, and your compiler is interacting with this different stage of the code model, and then your source code pass here doing compilation over here. So this, if you look at it remember the one we talked about early? So it's somewhat like the one we talked about. You have the regular expression pass through a flash, okay, and then generate this scanner, and then you have the content-free grammar, and then go into Python, generate your parser. Okay, you do this and then zero stage, something like that. Okay, simple table here, and you have input, you have output, right? So this input output they put it over here. If you see it actually here, going up and going down here, and then this whole thing here is this one, and the yellow one on top of it is here, and your input language is here, and target machine description is over here. Is that okay?
Yeah.
Similar structure, okay? If you look at it, it's actually similar structure. Okay, similar structure. So data flow view, okay? So these different languages. So your front end, you do C, C++, Java. Java is also one of them, okay? Language supported. Ada, Go, whatever different language. And then it will generate AST, okay? AST, you got AST. And AST actually built into a generic model. Okay, after here, you actually don't see any language now, right? It's abstract syntax tree, okay? That's the syntax tree or AST. Generic provide language independent way to represent the function of the tree. So once you are here, actually language is independent. And then you put it into Gimbal, doing Gimbalification, okay? And then SSA stand for static single assignment. Okay, here is actually some form. We'll explain it later. Okay, and then you go into many optimization paths. I told you 10 plus, 20 plus, 100 plus, depending on how much you want to do. And you do on SSA, so will be remove the static single assignment form. Okay, so here put into single assignment form, and then you do many optimization, and then you return to the regular form. Okay, here is a expand and reduce process, and after that you go into register transfer language. Okay, so you already know that this register loaded to here, to the processor, to it finish, go back to a certain register. But this register maybe is just unoptimized. Okay, so going to back end, the instruction set still will optimize it. So basically here, two optimization we talk about. One is in the front end, you do some sort of language independent optimization. Then in the back end, you still have the backend optimization with the machine dependent optimization. Conceptually is different programming language generated SST and then go into a single register transfer level form and then provide it to assembler. Is that okay? Conceptually.
Yeah.
Yes.
So here are the important passes, okay? And here you will see different strange name. Okay, different strange name. Okay, this strange name just tell you it's actually a different file format. Different file format you will have, okay? So there's a gimbal file, there's a CFG file. One important thing here is like this CFG is not content-free grammar, okay? This one is not content-free grammar. You can think about this as more like a AST. The name is not content-free grammar. It's called control flow graph. Okay, it's called control flow graph. It's not content-free grammar. It is the result of using content-free grammar and generate some sort of decorated tree, but we call it control flow grammar. Graph. Is that okay? Control flow graph.
So we use a CFG to generate a CFG.
Some sort of, yeah, like a version of CFG. Well, actually, different name. Yeah, different content, but same name somehow. Some acronym. So here, that's actually CFG grammar means this one, means the control flow graph, okay? And control flow graph actually is a decorated syntax tree with loop. So you see, it's with loop. So it's different from syntax tree as well. Syntax tree have no loop. So here you will see AST column whatever dot origin. That is the first version of the syntax tree you will get. So this actually is file format. Is that okay?
Yeah.
And then gimbal file format, and then CFG format, and then RTL format, and then this. Why we talk about this? All these can be dumped. You can dump that kind of code by GCC compilers, okay? So first one, this one called AST dump, okay? Test whatever. Let's just try. I don't know whether I can be successful or not. I haven't checked my GCC compiler for a while, but let me try, okay? I can guarantee it will be successful because I probably never tried it for maybe, let me create something here, call it GCC. Okay, go into here, okay. That's my directory. So here, you can have different compiler, okay. So here, let me actually bring up Notepad++. I don't use IDE, okay. Actually, I use a lot of IDE, but not for this one, okay. Usually, it's better using Visual Code right now to be more efficient. So here, let me see. So change it to C code, okay, C code, C source file. So that's call it test, okay. Okay, let's do include. Okay, integer name. Okay, what do we have here? Oh, there's an integer a assigned with 55. Okay, let me actually comment this guy out. Okay. To be, I'm sorry. This one, let me see. Okay, let me see. We got this one. Let me open my notepad. See. Okay, we have that. Okay, good. So here I do Window R, bring down my command line. Okay. Over here, let me change to that already the CD. Go here, left click, right click, copy. Okay. Put it here. dir. Okay, I have the test.c file. Okay, let me do this one. Here I have gcc-dump, whatever. Okay, I must type it correctly. Okay, so we will see that. Let me maybe it's too small actually. Let me actually minimize this one. So I have gcc-f dump, file dump, okay, -f dump -3 original -row test.c. Okay, go. Okay, so let's see. We finished that. So we got this original. Okay, this one. So actually, it create a application as well, right? But we are interested in this guy, right? Is that okay? Is that okay?
Oh, yes.
Yeah? So the reason why I spend so much time on this front end look like nothing to do with the textbook, but it will teach you a lot of things. Okay, it really will teach you a lot of things. So this is a dump file. So this dump file actually is this AST original. Okay. And what do we have over here? It's actually 3 original not declaration. So you see that his expression, void type, name, whatever, parameter, whatever type, okay? So type at 2. So this probably tells you what it is. Is that okay? So identifier, whatever, call, argument, whatever, let me see. Can we figure out something? Main, right? We see something main, right? Return type, right? Is that okay? We do see some, so the main program is over here. Before that, there is some other things being, so I think it's actually a what? Smaller item over here. It's actually your declaration tree, maybe like this, right? So top level actually written over here. Because your main program is over here. Is that okay? And then the lower portion, the deep portion or branch portion, you put over here. Is that okay?
Yeah. So it the file kind of goes in backwards order in relation.
Yeah. And you see that there is a at the 26 actually is this guy. You know what I'm saying?
Yeah.
At 27 is okay. So well, I do not intend to teach you everything to understand, but just that you know this is some sort of dump file we got from the first declaration result. Okay, so whatever here, second half, blah, 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 I talk about anything, it would be this. That's the real thing here. Is that okay?
Yes.
In the real world, we're dealing with something like this. And whatever we may be talking about here is actually theoretical and doing this, that, whatever, you know what I'm saying?
Yeah.
Okay, that's the first stage we have. So that's why I told you I want to do this first instead of talking about those grammar, okay? Grammar is easy. You talk about it, you spend 2 hours, 3 hours, you still don't see any real things, right? You still cannot see any real stuff. So here, that's the first stage. We actually do syntax tree. As you can see, it's somewhat like generate a simple table, right? It's somewhat like generating a simple table. And then you kind of having the simple table and then kind of knowing about first process. And actually there's no evaluation, no action involved, right? It just look like generate some sort of simple table. Okay, so that's the first step we got over here. So we have that. So, excuse me. So that's the AST dump. Okay, first stage we dump AST. So after that, we actually have the dump, and we do the second stage called gimbal. Okay, so gimbal actually is from the .test file. What we will do actually is we need to assign to some temporary register and variable. So you see it's no longer A, it's actually something like this. okay, D whatever, and A actually. So these are temporary variable, and A actually. I think it's actually, okay, this is a different test C already, this different test C. So it has some array and some assignment, okay, and then generate something like this. Is that okay? So this one actually is to work on this. Is that okay? So let me call this a test C as test2.c, okay, to have a difference. So let's go to this guy, okay? So now we are done with this. Let me close this one. So let me actually create a new one. And this one, let me actually save as same directory, but let me call it test2.c, okay? Here, let me change to C format over here, okay? So test2.c, let me don't have the C, okay? Save, okay? So that's my test2.c. So over here, I don't put the include anymore because include will put more code into there. So that's not good for us. So we have integer a3 and then x and then a1 equals a2 equals 10. And then we have x equals a1 plus a2 a0 equals a1 plus a times x. Okay, let me check. This. Okay. So can you understand this code? So this one is you declare an array of 3 elements, right? Be careful, in C language, this one actually put into step. So here you have 3 integer over here, okay? If you create this one, it is 3 integer, and you also have an x. This is in my main function, okay? But in Java, if you have an array will be put into the heap, okay? So actually it's different.
So is this why in Java you can dynamically grow arrays, whereas in C you can't, and they're of fixed length?
No, in Java they are fixed length
in
too.
Java you cannot dynamically grow the array. No, in Java you can reassign the array, not. So in Java you do integer array A, right, equals whatever data. Okay, later you can do A equals new integer. Say for example, originally you have 5 elements. You can reassign 6 elements or 7 elements. That's not grow. That actually is reassignment.
Okay, maybe that's what I'm thinking of. Maybe I'm misremembering that.
But that actually is 1 5 element, 1 6 element. Originally you pointing to here, but later you actually reassign it to a different location. Is that okay?
Yeah.
That's one difference. Second, this object actually always there as long as the array being created. These one are not. Actually, it's only a local variable. When you get out, you will be dead.
I was wondering, you said it's the array in C is on the stack. What if you declare more than one array? Is that how is that handled?
You declare what?
You declare a second array, like integer b of size 3, for example?
If you want to have a array that actually is of different, if you want to actually declare an array of, say, you can do C, right, and you do C, actually start integer, and then you do this, it's okay. Right, you see this, right? Is that okay?
Okay, so you can't simply
this one actually is dynamic array, dynamically allocate the array in heap.
Yeah.
This A array in stack means that when you get out of this function is stack, it's no longer there. But this one actually is always there. So if you save this address or pass to other address out of this function, the object's still there.
Okay.
Is that okay?
So you can only have one array like the A array?
No, you can also do B array. That is also legal. But the problem is that you don't want to put too many items into your code frame. You put too many items into there, you will grow too big, and then you will face the stack overflow problem earlier.
Okay, I see.
You know what I'm saying?
I did some Googling and I figured out what I was thinking of earlier. I was thinking of the Java array list instead of the normal array, which you have to import. So that's where I got mixed up.
So as you can see, C has more flavor of the array. Even though the teacher doesn't usually teach you that these are of different flavor, but they are of different flavor. You can have the dynamic allocated one, you can have external one, you can have the local one, actually depending on how you create it. You know what I'm saying? Okay.
Yeah.
Okay, let's see. That actually let's go back to our topic. So here we have everything we need, right? So we have everything we need. So let's go back to here. I have this now. So here I'm going to do a similar start to generate the file. Okay. So you see the file. Well, the format over here actually is simplified, right? It's not the same as what you would see. So here, let me actually do this one. That's why I want to show you once, and I'll send you here. So again, it's a file type, okay? These are different type of file type, and you do 3, and then Kimball type, okay? So Kimball is doing what? Kimball is actually create a temporary variable for you, right? So temporary variable we created because what? Because we are going to actually allocate the memory space, memory location in the real assembly for you. Is that okay? So previous stage you do the AST, and the AST actually has a declarative and the tree structure. There's a tree structure, right? And here you create some register structure for it. Okay, so let's see here. We got this, and let me open it. Okay. So now we have two gimbal. Okay, we got this. Is that okay? As you can see here, it actually added in some try finally for you. What's try finally?
Oh, I know try catch, and there's a I don't see why there would be a try final without a catch.
It actually is similar to, it actually, you do some call, right? And you do, this is called try block, right?
Yeah.
When there's an exception, you go into a catch block, right? So you catch some exception, whatever, right?
Mm-hmm.
And you do catch block. So it's over here, it's emergency box. So when you finish, if you don't have finally, you will go here and then to meet here, right?
Yeah.
Finally, actually, is over here. So both exceptional case and unexceptional case will meet here. So this is finally box.
Yes, but when you
so finally, the main purpose is to what? To clean up whatever error flag or your rollback stuff over there. Is that okay?
Yeah.
Yeah.
But if
so,
there is no catch, then what's the purpose? What's the point?
So very few people use it. I mean, So you rarely see finally. But if you actually go to here, you do these language structure actually have been there for maybe a long time, but finally is something that people now really favor to write it. You know what I'm saying?
Oh yes, I understand that finally after the catch. I mean, if something happens, some error happens.
No, actually, it's of no purpose. That's me that draw the diagram for you. So here you have try and catch, right? So here, if there is a box, you do this, right? Right? And then what's the difference that if you actually don't have finally and you do this? Actually, it's the same, right? So finally, actually, just a language structure that actually you can mimic by without finally. You know what I'm saying? You actually have no special meaning. I just delete it. Will they do the same? They'll do the same.
Yeah.
Yeah, so it's use this language structure. Is that okay? Some people invent that a long time ago and have been implemented for a while, but eventually they find out that it's actually totally useless. Is that okay? Okay, yeah. Anyway, here gimbal stage is what? The AST stage, you generate a tree and then put them into some sort of file over there. And then here you create something like register and variable. So here closer to RTL, but unoptimized. Okay, so and then you go to the next stage, abstract syntax semantic graph. Okay. So why is that? You actually do semantic analysis, you do identification, check the type, and then create error message if the type is wrong or value out of actually not acceptable, something like that. So you do lexical analysis, syntax analysis, and semantic analysis. So after here, you check all the grammatical errors, and then you will create a decorated AST. You can think about this one actually is the AST format we got, okay? It's an abstract syntax tree. That's the format we got. We got over here is a format we got over here, but not exactly the same. Okay, from the textbook point of view, the thing that they talk about decorated tree is actually more complicated than the AST. Okay, we can only say that the first one, this one is a very simple one. Okay. Okay, it's a very simple one. But later we'll generate something more complicated called ASG. And that one is more decorated. So AST is decorated but less decorated. I can only say that, okay? And in between here, sorry, we have several different stages to generate from a tree to graph. So graph actually means they are loop, right? They are loop. So because they are loop, so what I say is like the ASG is somewhat more closer to this guy, more close to this guy. So this is a real name, and this ASG is a academic name. Is that okay?
Yes.
Yeah.
Yeah.
And so then we have single SSA, static single assignment. Who like this SSA? Who look like this guy? Gimbal look similar, right? So Gimbal is a stage before SSA. So Gimbal have A equals 3, B equals 9, C equals A plus B, and then A equals B plus 1. Static single assignment means let's do this. my A show up 1, 2, 3, 4, 4 times, I will use A1, A2, A4, A4. I will use each one. If it is on the right hand side, I can use the same one, right? Is that okay? If right hand side and left hand side, I can use same one. But second occurrence, I assign a new value to it. I call it A4 already. Is that okay? So left hand side, I cannot allow it to happen 2 times. This is called what? Well,
what is the problem with that? With the
we just want to expand it. We just want to expand it to here.
Okay.
Okay. Why not? It's not because we want to make some grammatical improvement, but because we expand it and we optimize it and then we unexpand it. So there's a unstage over here.
Okay.
You want to say?
Yeah.
So we don't know how to optimize. So we originally have 5 lines of code. That's expanded to here, but eventually we are going to shrink it. Is that okay?
Yes.
And I think they try to find out the data dependency in this different variable assumption. So they actually, every variable is assigned only once. Assign only one means the left-hand side you can only show up once. Is that okay? Can be used for read-only value multiple times. So read-only is right-hand side you can show up many times. Is that okay? Left-hand side 1 time, right-hand side many times. That's okay. If statement merging taking place with a 5 function. So each one of the, if there is a 5 function, and 5 function evaluate the branch flow. You can evaluate this one and this one, create a 5 function. Is that okay?
Yes.
And then GCG perform 20 optimization over the SSA tree. So SSA itself is a tree. So you simplify it, have simple variable assignment. So it's somewhat like a simple RTL. But after that, you expand it into SS tree, and SSD tree go into 20 plus optimization. Actually, right now may go to 100 plus already. Is that okay?
Yeah.
And then after that, you do SSA and go back to real final RTL. Is that okay? So it's somewhat like create initial set of RTL, expand it, optimize it, and then go back to a final format. Is that okay?
Yeah.
And why these smarter guys do this? Okay, there are some detailed story you can find, maybe 20 different or more technical paper to know it. Is that okay?
Yes.
So I told you like actually in the syllabus I told you you have Java 1, Java 2, and then C1, C2, and then Python 1, Python 2. Right over here you have data structure algorithm, right? And here you have this programming language. The next one, the king of programming, will be compiler design, right?
Right.
Yeah. It's hard, but it actually is a good course to take after this programming language, okay? You will have to, this one is conceptual course. PL is a conceptual course. Compiler is a hand-on course. You need to get your hand wet to actually crank out every single line of code for it, right?
Right.
Yeah, and this one we do not intend to teach you those kind of things. So from the so-called SSA, going to the next one, you got this one CFG. CFG actually they will allow loop already, so they say if then else may go back. So all of these, those while loop, for loop, whatever will be like this. And why here we put a if? There's no while or something. Why? You may have looked, right? And why is always if? Because later when you go into assembly or even go into executable code, you'll be jump greater than, right? Jump equal, right? Jump unequal, whatever. Is that okay?
Yeah.
So these are all if, right? You no longer have the while. It's jump on condition, right? So if condition will do something, if condition. So that actually is what is over here. And we actually will, from CFG, will create SSA because we want to put a file function into there. Okay, file function is actually evaluate the alias. Now your A register actually have A1, A2, A3, A different left-hand side symbol. Is that okay?
Yes.
So CFG is one stage before complete SSA. And SSA, we have test file, we generate this in Kimball. So CFG dump. Okay, how about this? That actually do the same program test 2. Let's do CFG dump, okay? So here you see always 333, okay? So not too difficult. Code file dump and test.c, test2.c, okay? We want to have that one have an array type, okay? Good, let's see. Yeah, so here you see one loop found. Okay, this so they are labels. They are labels, right? Let me see. They are labels, but actually there is no if statement. Now let me try different thing. Okay, this one doesn't show the. This one doesn't show me the what I want to have. It has no branch, so it's not actually good for us. So let me actually bring this one up. Okay, here I create a new one. Okay, we have some sort of loop over there. Okay. Test 3, okay. We have some sort of loop over there. No such file. Let me see. Oh, okay. Sorry. We have test 3. Yes, we have test 3.
You were missing the dash on the command line.
Oh, okay, okay. Yeah, sorry. Yeah, good. yeah, I start to have a loop, right? And they are loop level go to thing, right? It's okay. And there's a if function, right? You see that?
Yeah.
So there is no longer while loop. You all go into here like this. Is that okay?
Yeah.
Yeah.
So here I think this one is discretion for the first loop, second loop. Okay, whatever loop it has. It's here loop may not be really the loop. Actually, sometimes it may just be a if or something, some go-to function. Okay. So function main, whatever. Okay, this is simple table. So there are something you need to check the dump as well. Okay, change the AST. So here you should also do this one. GCC does F dump dash 3. Dash origin dash row dash 3 dash C. Dump one thing is not enough, okay? Because that one you have to actually also work on this test suite original. So some of the name over here may be used over this dump CFG, right? You have to check it. Okay, anyway, that's after GCC, you actually have some translation and their labels, their branch condition will be generated, but it's not called branch. It's actually if something go, somewhat like a, still be in C language style. And then you go into RTL dump. Okay, so let's try this RTL dump now. So now we do expansion and then optimize and then unzipper, and we are going to here. Okay. So here the next one is to go this one, RTL dump. So GCC to F dump dash RTL. So it's no longer tree. You go expand test C. It's no longer tree. It's now RTL. I need to do test 3. Okay, I would like test 3 because there are more contents. So at this stage, to do open, to do expand. So as you can see, actually every stage they have something there, and this guy is what? This guy like what language?
Looks kind of assembly-like to me.
No, it look like Lisp.
Oh yeah, because of all the parentheses.
Is that okay?
Yeah.
It look like Lisp now. Okay, so this RTL dump actually look like so basically it's more like functional description for the different things. So it's quite complicated. Okay, so why is doing this in here? I think there are some theory behind it, very difficult one. Okay, so not easy for her to understand now. So anyway, here you go into that RTL expand, and then we can further actually do dash S and dump this whatever. Okay, let's try this one. Assembly dump. Okay, this one is assembly dump, and here I think actually it also compiled to the output code. So that's not doing the second half. Okay, doing the first half now. So GCC dash S and then test 3.c. Okay. So here actually is next stage. It do compilation, but it actually do some sort of dash S, and let's see. It's test S. It will be assembly code now. Is that okay?
Yeah.
Yeah. So assembly code is maybe combine of all the format before or whatever. Now you go into a assembly code now. Okay, next one. Let's do this one. OBJ dump the dash out. Okay, so I think it's actually GCC dash S test plus 3 dash C bar and then OBJ dump dash DA dot out. Yeah. Okay, open. Let me see. Oh, actually, you create this one, A program. You create the A program now, right? Actually, that's the goal. You create the A program, the executable file. Is that okay? So here, dash S, we got this dash S, and that's assembly code. Okay. Is that okay so far?
Yes.
Okay. So this
Yeah.
actually, I try spend some time just to let you go through the whole compiler flow. And knowing that there are several detailed formats. And as for each format, what will they work? You really need to study the compiler to know those details. Is that okay?
Yeah.
Yeah. So can we have a 5 minute break? We'll be back 11:12.
Yeah, that sounds great. I need more coffee.
Yeah, and we will get started for the next section because it's different thing. Okay, we started to have a semantic flow. Okay.
Right. Sounds good. See you in 5.
Yeah. Hello.
Yeah, I'm here.
Okay. Let me see. Is Nathan back? Hi, Nathan. Are you there? Okay. Wait a little bit. Okay.
Yeah, sure.
Hey, I'm back, guys.
Okay. Okay. Good. So first half we talk about the flow of a compiler, right? Now we are going back to the theoretical study for the semantic analysis, and it actually will be, we know this better now, so actually is kind of doing mainly this one over here, okay? This portion actually, we do a little bit, but not too much, okay? Maybe up to here, nothing here. Here, 0, okay? Here actually is optimization, actually generating the intermediate form. So this part 0. Okay, so basically we are maybe 80% over, maybe 90% over here, only 10% will be covered this, okay, starting from here. For all the theoretical things we talk about, something like this. And then we talk about the other thing called ASG. So ASG actually is the end result we will get, okay? Theoretical result we will get. And it would be something similar to maybe this guy, but we do not touch the SSA things here. In the theoretical study, we do not touch the SSA thing here. So today we are going to start this semantic analysis. I'm trying to finish up to this L shape, L attribute SDT, okay, up to here. And then how to evaluate it would be the maybe Wednesday job. Is that okay?
Sounds good to me.
That's about it. Okay, that's the Wednesday job. We will start there. We are kind of a little bit slower this year, but I want to make sure we do things right, okay? So following the passing, the next two phases, typical compiler will be semantic analysis and intermediate code generation. Yeah, that's what we see today. The AST generation, the gimbal, the SSA, the un-SSA, and then go into, in the SSA, we do optimization, and then we go into un-SSA, and then go to the intermediate code RTL. RTL, you can think about it, actually is intermediate code. Okay, the principal job of the semantic analyzer is to enforce static semantic rules. What is static semantic rules? Static semantic rule means integer a equals 3, integer b equals 0. These are okay. These are okay. And then you do integer c equals a divided by 0. So this one semantically is now okay. You have division by 0, but this won't be catched by this static rule. Is that okay? It won't be catched.
Yeah.
Okay.
Yeah.
And also something like this one, integer array a equals new integer array 5 element, and you do a of 6 equals 10. This won't be catch. This compiler just say, oh, okay, integer, good, pass, right?
Yeah.
But wrong time you see the index out of bound problem. Okay, array index out of bound. So construct syntax tree usually first, and then gimbal, CFG, SSA. Information gathered is needed by the code generator. Okay, so SSA, this kind of information, plus IR format, these two are actually files, right? As we see SSA type file, CFG type of file, and then assembly type of file, IR. These are the information needed for the next stage. Okay, we talk about file formats. So we construct syntax tree these, and then generate these ready for it. intermediate code generation. So there is considerable variety in the extent to which parsing, semantic analysis, intermediate code generation are interleaved. They are interleaved. So conceptually, we talk about this maybe 3 different stages, but it's not. Actually, it's actually being mingled together. I mean, you cannot actually really tell which one is semantic analysis, which one intermediate code. And in reality, it would be better that you, when you study compiler, it's something like this. Okay, different compiler actually do different things, but some compiler do this first, some compiler do that first, and then it really hard to actually tells you which is what stage. Okay, common approach interleave construction of a syntax tree with parsing, then followed by separate sequential phases of semantic analysis and code generation. So common practice is give me a tree first, and then let's actually do declaration, and then do code generation, and that maybe have several steps and several sequence. Is that okay?
Yeah.
That's common practice. And there are so many flavors. So here we just talk about the guideline, not actually talking about every single compiler should do what. Okay. Semantic rules are further divided into static and dynamic semantic. Okay, we talked about it already. The compiler enforces static semantic, and compiler generate code to enforce dynamic semantic rule at the runtime. Okay, so it doesn't check it, but it actually generates code to enforce this. Okay, what that means? Actually, if, for example, we have integer array A equals new integer 5, right? For example, like this. So here we have an A of 6, right? Doing something. So once we do this one, at the compiler stage, it will maybe, here you have temporary variable, so you maybe have D5555 equals 6, right? So here it will be check D555, something wrong, and then it will say, actually, I mean, greater equals 5. Then it will actually do exception, right? Is that okay? Something like that. So your real compiler will insert that code in there. Is that okay?
Yeah.
And so this is going to happen at compile time or at runtime?
Compile time. To enforce the check-in at runtime, but actually compiler enforce it. So you run this code really at runtime, but to insert this if in there, that actually is compile time insertion.
Okay, I see.
Is that okay?
Yeah. Yes.
Yeah. And type checking reporting error as semantic as analysis stage. Okay, this actually is to check every variable. So if you have the array and then you do array of a character, or you do array of a string, sorry, that will be checked, right? That actually compile time will find. Both semantic analysis and intermediate code generation can be described in annotation declaration of a parse tree. So here, the input is a AST undecorated, output would be decorated AST. And this AST can also be called AST, depending on you have loop or not, no loop, right? And also this thing actually will involve also gimbal things, whatever. So here actually conceptually is like undecorated and decorated, and decorated may have graph, then it will be AST. Okay, so decoration are attributes, attribute is what? Attribute is, here you have A plus B, and it actually is an ID, and actually it actually is a integer, whatever. These are the attributes associated with this node. It's okay. And synthetical analysis, you generate a tree, but you don't have this kind of information. Now we are going to put that things over here. And this is a executable call, so it will actually decorate it as an operator or something. Is that okay? And then also add in the evaluation function to here, in order when you actually do running, this will be evaluated by plus something here. Is that okay?
Yes.
Yeah.
So that's some kind of the declaration we talk about. So most of this chapter is actually devoted to attribute grammar. So attribute grammar means the grammar you use to describe the attributes, right? So not hard to understand. So attribute is the declaration things. It's something you want to put on your Christmas tree, right? So that's a thing that you have a syntax tree. This one is that your Christmas tree, right? And we do decoration. So each decoration, put in some bell, whatever over here, right? That's your attributes, right? You decorate your Christmas tree, and then whether that it's actually okay or not, that we actually have an attribute grammar. So this one may be what the JIS, Japanese standard, American standard, whatever you need to follow the rule, right? Is that okay?
Yes.
And the end result is the decorated Christmas tree. Okay. So attribute grammar provides formal frameworks for the decoration of a tree. Topics in this chapter including attribute grammar, attribute flow, attribute routine, and tree grammar and decoration. So here the last three are for the next time. Okay. Today we only talk about this attribute grammar framework. Okay, it's a useful conceptual tool, even in compiler that do not build parse tree. Okay, are they compiler do not build parse tree? Yes, but very few now. Okay, very few. Probably very simple compilers. So we have static versus dynamic semantics. Static grammar, we have the attribute grammars, and then dynamic semantics involve abusing operational semantic, axiomatic semantic, denotational semantics. So here, actually, these are not going to be discussed right here, but there are more rules over there. Okay, so we have static versus dynamic. We use static to describe property that compiler can determine without considering particular execution. So no particular execution involved. So we define this. This one is a static thing. You just return, just perform x plus 1. Okay. So if you have the division that will create exception, then compiler could only deduce them to be integers. But I mean, the language design that require us to work on the variable only, okay? So something that operational, you will not be able to find. Is that okay? So you only declare a tree, but the tree threatened to call and call being wrong beyond its capability, okay? Okay,
yeah.
Anyway. Many compilers that generate code for dynamic check provide option of disabling if desired. So here, not in Java though. Java actually do not actually welcome you to do that much. Well, Java may have the option flag, but people use IDE actually usually don't find it. Okay, so there is something you can disable, something. I don't want this warning, I don't want that warning, I actually allow this. I mean, it actually, you can have the compilation flag. So in the old day, we have a tester, QA people, and we also have software engineer to do integration. Is that okay? And they know about tons of flags, hundred different flags, and use the make file. Okay, is that okay?
Yes.
Yeah.
Actually, my wife's job is working as a integrator. She worked on integration for 20 plus year now. Okay, work for Synopsys, a EDA company. Okay, leading EDA company actually. Synopsys.
What is an EDA company?
EDA is you build the IC for you. You actually do design and then they generate it. So let's do.
Gotcha.
So you do kind of writing Verilog and to generate the layout is called layout and then schematic. Okay.
Gotcha.
So
very cool.
These kind of tool is called. So actually, usually their database is very huge. The database is usually very huge, and also tons of code involved. So I heard from her that actually I heard from her that some of the program maybe a few hundred or even thousands of the modules. So
wow,
they just
that's intense.
yeah they make file actually sometimes need to run several days to in order to get it. Okay, and every day they are building program for people. Just hit a GCC something like that. You know what I'm saying?
Yeah.
Yeah, the job actually is very tedious and very need a lot of patience. But usually it's good for some retired developer to do that.
Yeah.
You don't like to do R&D anymore, but you actually have a lot of experience, so you can help to build a bigger program. And they have top level view better than the individual R&D engineer. Okay. So it's customary or whatever. Okay, check that during the test that disable production rule. Okay, some of the thing you actually need to disable for production rule. So you have something like okay, you print out then you don't want your customer to see it. You have to disable it, right?
Yeah.
But you can use the when you do debugging anyway. So nothing funny to show up. Okay. So errors may be less likely to in production than it's in testing. So that version is very important. So here we talk about when you do dynamic checking, you do want to put more feature into there to make sure you have alpha version what you have, beta version what you have, production version what you have, right? And your production version may not be the same as beta version, may not be the same as alpha version. So beta version, you may want people to send back email or send back something, inform us, okay, production, even there is a bug, they probably don't want you to do that, right? Or they will ask you, okay, do you want to join us for the program to help us to debug? Yes or no? Yes, you probably will generate that. No, maybe not, right? So production variable, you have different consideration. Okay, whatever. Here, just talking about dynamic checking, how you deal with it, and from compiler point of view, what you do. So here we have assertion in Java, but nowadays very few people do assertion. Most people do exception. Okay, but assertion is a statement that specifies condition to be met. Okay, is that okay?
Yeah.
Let's
Yes.
try this guy. Okay, let's try this guy. Assertion in Java. Okay. Yeah, so actually sum of 1 to 10 actually is 55, right? So here if I actually do 45, so I have assertion. Let me clean it wrong again, okay? So actually you do not see the I'm here, but actually break and had the assertion error. Is that okay?
Yeah.
Yes.
Yeah, so this actually, well, it's a way you do it, right? So here if I have integer n, right? So here I should have, say, I can have equal 0 here, okay? And I do for int I equals 5, I less than 50, I plus equals 5. So every 5 I do sum equal these. I use this equation, so it will be working on all of the different sum result, and we do it, and actually you do this one divided by 2. Okay, I'm sorry. So let's do this one. I'm sorry. Okay, I'm sorry. I actually do this one. I equals n total n, so 0 to, okay, here's not 10. Let me put an n over there. Okay. So clean this one. Here let me do system. So I changed this one to calculate the sum of I. Okay. So these two I are actually different. Okay, two I are different. So I pass 5, pass 10, pass whatever, and check in with the equation. So everything passes. So I see I'm here over there. But if I put the wrong equation, then you will have your assertion error, right? Is that okay?
Yes.
Yeah.
Yeah. So this actually is what we have over here. So here, let's see. If I don't do this equation and I actually do here, so let's don't do to 50 too much. Let's do to 10 only. Okay. So two variable. So integer static. Let me see. So here actually let me do I equals 1, I less than 2, and I actually plus plus. So here I do I times 2, okay. So that would be I times 5, okay. So here I have, let's do integer x equals I times 5. The total of x, and here x over here, okay. So here I can change it to static integer array of the so-called answer equals sum 1 to 5 actually equals 15. Sum 1 to 10 equals 55. Okay. So the two value, let me see. And here it should be equals answer of I minus 1. Okay? Is that okay?
Yeah.
Yes.
So I don't hit it okay, right? So if your answer is the same with these two answers, it will pass it. So this is actually a text vector, right? You use different value and you feed it and use text vector to test it, right? But the problem is here you have something wrong. So your calculation may be wrong, but here let me actually change the answer. So if the answer is wrong, you will catch it, right? But the problem is the program will be dead. If you do this one using a form version, okay? If you do a third version, it will be, so let me actually do this one. Yeah, I put 14 here. So you have the one correct version, one wrong version, but your program will be dead because you cannot pass it. So assertion recently people don't like it. So we modify this one to exceptional case using exception. Without trying. Okay, so here one simple testing I write into this, but I have some advantage here, okay? So let's see. Here, let me actually still put in the wrong case, okay? So when the wrong case being wrong, let's see what happened. Is that okay?
Yep.
Yeah. So
Yeah.
let me actually, if I finish this testing, so I try this just to actually to show you when sometime later if you are actually asked to write text vector and how to actually provide a program so that actually you can do automatic testing and you can provide each test case result. You know what I'm saying? Is that okay? That's why I'm doing this here. Okay. So use exception is better than not. And beyond this, actually, you should also try to use JUnit. You know what I'm saying? JUnit, PyUnit, whatever UNIT code here. Actually, you can do create test class. That would be a UNIT test class alongside with you. And here, this one beyond my main topic right here, but you can try to create a test class associated with it. The reason I like this BlueJ is actually a graphic tool, and for high school student, early college student is actually quite a good tool compared to just do complicated Eclipse tool. I mean, that's for engineer, not for a student. Okay, so here we finish this one assert. I just want you to know that there is some way you can actually do it in your program. Okay, to do meaningful thing. Assertion in C++ similar. When you assert fail, you will break. Okay, but nowadays everybody go use a try block. Okay, try catch block. Static analysis in general, compiler time algorithm that long time behavior we call are known as static analysis. To predict runtime behavior, we call it static analysis. So they are type checking, alias analysis. So this type checking important. Alias analysis, escape analysis, subtype analysis, optimization, and optimization including unsafe code leading to. So this one is original warning. Speculative code, improve performance, but downgrade sometimes. You may declare this. If not wrong, you still want to do this. Conservative, okay, for sometimes they actually inform you that for integer I, you forget this, whatever. They may give you some idea to keep it safe. Okay. So the compiler may also have something that's beyond syntactic error. So this may be reducing the number of runtime errors. So whenever you have something divided by 0, they may inform you. Okay. For some kind of compiler, not everyone. Okay, attribute grammar. So let's look at attribute grammar. Let's see. Okay, both semantic analysis and code generation can be defined in terms of annotation. So here, attribute grammar is the rule to write the attributes. Okay, an attribute grammar provides a framework for decorating such a tree. The note below discuss the attribute grammar, ad hoc cousins, and action routine. Okay, so we start with decoration of parse tree, then consider syntax tree. Okay. So let's look at the parse tree and then the different grammar for it, okay? The attribute grammar serve to define the semantic of the input program, okay? We know this. Attribute definition, assignment, we know it, okay? Let's look at example. Okay, here. We have a grammar that is on the right-hand side. Expression equals expression plus turn, expression equals expression minus turn, expression equals turn, turn equals turn times factor, turn equals 10 divided by 10 factor, 10 equals factor, 10 maybe equals minus factor, or 10 may be operation with expression, factor, and then factor may be a constant. Okay, these are the set of rules of ETF, basic arithmetic rules. This grammar will generate properly form constant expression over basic things. Okay, here, okay. So we got this. Now we are going to introduce the simple S val. Okay, it's S value. Okay. So basically, we would like to generate the derived S form. So we assume that the value of a constant is provided when we do scanner. Okay. So this thing can be written in attribute grammar like next one. So left-hand side is the grammar we have. Right-hand side is the attribute grammar. So each dual associated with the evaluation function. Is okay? So right-hand side result evaluate to left-hand side. So you actually do something. So once you see a E, say your E1 node, you have a expression 2 with the terminal, and then this one is a factor, and this one can be a terminal, term, and then factor, whatever. So this actual factor would do evaluation to assign F value, and F value evaluate to T value. T value and this E value together evaluate to this E that value. Is that okay?
Yeah. Yes.
So this is actually decorated so that each term on the tree has some evaluation function. So this is so-called attribute grammar, help you to actually doing the evaluation. Is that okay?
Yes.
Yeah.
To be short, add equation to the term, right? So that's what I say, E1 equals E2 plus T value, right? Conceptually something like this. Is that okay? So some difference, some product, some quote, some derivative, assign value to it, right? Not hard, right?
Yes.
So this is not hard to understand. Just based on the rule, saying right-hand side will produce what result to the left-hand side by the semantic. Semantic actually, semantic means value, right? Right?
Right.
Right? Maybe, I don't know. So if I say this one, my wife's name is Christina, so let's say the value is this guy, right? That's the semantic, right? But when you use a different program, oh, okay, I love you means different person, right? Maybe every day you change the you, right? I don't know. I'm kidding. Attribute grammar relax. So here in the strict definition of attribute grammar, copy duals and the semantic dual, semantic function call. So this one, I see. So L equals IT and L. So this one is actually the so-called IT comma IT list. So here list tail, list equals list IT and list tail. So here actually, let me see. This one is list. List is ID and concatenate with this tail. So this plus sign actually is concat. Okay. Right? Is that okay?
Makes sense. Yeah.
Or if you use it as a counter, then you count how many symbols are there. You can use a plus. So relax in the strict definition semantic function. Okay. The symbol can be written inline. Okay, it can be written inline. You go to counter, comma separate. Okay, not important. Okay. So attribute grammar, okay, here are some guidelines for it, okay. The purpose of AG is to associate the meaning with the grammar. We can use any notation you like, okay, type, whatever, verify. Example 4.4, 4.5, we associate with, we associated numerical value with symbol in CFG. Here, CFG, I think is content-free grammar, okay. Here is not control flow or graph, okay. Okay, so here guideline for identify a reference to information in the symbol tree. For expression is type. Okay. Here it show you different things. But the guideline here, let me see, 4.4, 4.5. Is that 4.4? No, no, it's 4.4, 4.5, let me see. Not this one. Okay, I'll see. I will actually show you when I see it. Okay. Sorry. So here actually is a guideline, and then for ID, there's a reference to the table symbol. Okay, the symbol table. So when you do tokenization, you create a symbol table X and whatever value or Y, whatever type, whatever. You have a tree here, right? And you see a X will be pointing to here. If it's expression, so here you have an expression, so that maybe actually has a value. So here maybe is integer, and actually is type, right? Is that okay?
Yes.
Yeah.
Something like that. We will see this in more detail. So it's what this attribute grammar say. Attribute grammar. So it actually tells you that the declaration may have different type. Some with spell, some actually is a doll, some with different thing put it onto the Christmas tree. And it may have different type, okay? Attribute grammar is a special form of context-free grammar. Special form of context-free grammar. So it's a context-free grammar with declaration, okay? Is that okay?
Yeah.
Yes.
So actually it is a context-free grammar in a way that you have left-hand side. Right-hand side, you add value to it, okay? Okay, so attribute grammar is a medium to provide semantic to the context-free grammar, yeah? So we knew that. Okay, next one. So here you can write down in this way as well, okay? Where do we see this? Where did we see this one? Remember when I talk about Bison, yak, I show you some C file, right? Left-hand side is like this. Remember that one?
Yeah.
And some duo, right? Some duo like this. Right-hand side, you have action item like this, right? Remember that?
Yeah.
Yeah, so that actually is some sort of left-hand side reduction duo, right-hand side the action duo, right? So that is actually when you really see this kind of attribute grammar, it is in this format, okay? And this context-free grammar with those duo fit into Python and generate your parser, right? Makes sense, right? Right?
Yeah.
So you are writing your own attribute grammar and then fit that one to the Python. So the context-free grammar we talk about that fit into the so-called Python. Actually, they are attribute grammar. It is a special kind of context-free grammar. Is that okay?
Yes.
So semantic attribute may be assigned to their value from their domain at the time of parsing. Okay, whatever it is, actually okay. Okay, so attribute grammar carry some attribute grammar to the parse tree used for this and this. Okay, I think I don't go through these details for these two terms. Attribute grammar is a context-free graph of this one. Okay, whatever. This just define the data structure. Okay. Production rule is a set of predicates. Okay, a set of predicate for production, for expansion of the rule. Okay, this actually we know. So next one. Okay, this one important. Attribute grammar. Something is synthesized attribute. Something is called inherited attribute. So synthesize one. Left-hand side is the synthesis of the right-hand side. Means A equals B plus C. So your result of A is from A, B plus C. That 8 is your function. This is called synthesized attribute. Okay? Determined from the nodal child in the past tree. This is called synthesized attribute. We see that because we usually see expression equals expression plus T, right? Is that okay?
Yes.
So this is synthesized result, okay? Okay, we know that. So let's synthesize result, and the other ones inherited. Inherited are determined from past parents and siblings. So inherited attribute is from the parents and the sibling. Why is that? Some is this type of inherited attribute from parents. Expression equals expression plus 10. Expression equals expression plus 10. Another one, okay? If we all three. And the expression equals terminal. Terminal term equals factor. So this one is an integer, this one is an integer, this one is integer, this one is an integer, this one is integer, this one is integer, this one is integer, this one. That actually get from where? Your integer property get from where? From your previous parents' node, right? What I'm saying?
Yeah, that makes sense.
Makes sense? So this attribute type actually may go from this grandpa determined already, right? And if you don't obey him, you are out, right? Out of family, right? Some prince actually get out, right? I don't know.
Mm-hmm.
Yeah, you know what I'm saying? You don't follow my royal family, you get out, right? My royal family's rule, you have to obey. That's the type, the kind of inherited. Well, your highest actually is from inherited attribute. It's not synthesized, right? You don't collect text from your children, not synthesized. You actually inherit from your parent. Is that okay? These two are of different purpose, but one is called synthesized, one is called inherited. So you think about it, the one is from child, one is from parent, grandpa, grandma. Okay?
Makes sense to me.
Yeah. So synthesized attribute S from this, okay, this is actually easy now, okay? Remember synthesize from your child. Okay, so I don't spend too much time. Explain this to the inherited actually from what? From two sources. One is from your parent, one maybe from your big brother, sibling. I forget to talk about this. Why sibling? Why sibling? Here, some of them may be before it. So you have S actually create A, B, C, right? So your C type may be depending on A or B. Why? System that out the print line, you do double quote A plus B plus C. This P, C may be double, maybe integer, right? But when you do plus, this becomes string, right?
Yeah, that makes sense.
That is you get your property from your big brother, okay? Your big brother want to give you some money, that actually is fine, right? Actually also inheritance. Don't have to come from your parent, right? So actually that is inheritance. Is that okay?
Yes.
Yeah.
So synthesize from your children, you need to collect bottom up, right? And inheritor is top down, and sometimes your big brother also okay. And actually maybe big brother, maybe little brother, okay. Maybe little brother also okay. Well, there are some rule. Some compiler may like only big brother. Some compiler a little brother also okay. So, okay. So A get value from S, this, and B get value from it, okay? So as I say that the system that out the print line since actually is big brother only, right? Right? That do actually big brother only, not little brother. So expansion, you do reduction, okay, this we know, okay, it's not hard. Reduction actually we do summaries, right? So when the terminal is reduced, the corresponding non-terminal according to the grammar rule. Syntax tree, pass top down and left to right, okay. What's this? So actually our tree become attributed tree, okay. So this is easy. So here we have 2 plus 4, 2 times 6 plus 4n, and we have such an evaluation tree. Is that okay? So if you don't look at the VOL, since actually it's original parsing tree, right? Is that okay? If you don't look at the values in it is the original parsing tree. So syntax is the directed translation. That's called SDT. Okay, up to here we call it SDT, syntax directed translation. Okay. Anyway, here actually SDT means you have parse tree dependency graph evaluation order rules. Okay, it's another term anyway. So here this one more important. S attribute. S attribute you can talk about. You can think about it actually more like sans attribute. Is that okay? Sans attribute. So it actually is what? Synthesized attribute. But I call it sans. You collect money from your sons. Is that okay?
Yeah, makes sense.
Okay. That's actually S attribute. And the other type called L attribute. L attribute, I actually, my language, okay, not exactly the same. This from grandpa parents. This from your big brother. Is that okay?
Yeah.
My way to understand it anyway. So it's an L-shaped SDT. You need to remember the name, okay? Remember that. That's why I help you to understand what is L. L is from top down and also from left-hand side, okay? That's your big brother's attribute. Well, some grammar rules do accept the little brother to contribute, okay? So here we have the S shape. Remember this grammar type, and we have 2 types. We have 2 types. We have the synthesized one, that's S attribute. Inherited one, that's L attribute, okay? L attribute, actually, I talk about it, it is top down and then left to right, so it's like L shape, okay? And S type is actually, S attribute actually is from the sun. Is that okay?
Yeah.
Okay,
yeah.
So we actually finish up to here. Wednesday, we will go to evaluation, and then we will go to maybe chapter 5. Maybe go to chapter 5 on Friday. Is that okay?
Sure, sounds good to me.
Okay. Bye now.
All right, see you.
Have a good one.